If black holes really are the most extreme objects in the universe, what are they still hiding from us? We usually meet them as a scary word from science fiction. A cosmic mouth, a void that eats light. But tonight we're not here to chase horror or hype. We're going to sit down with black holes themselves, quietly, carefully, and watch what they actually do. How they're born from broken stars. How they bend space and time until before and after stop behaving the way your instincts expect. And why, in the strange logic of nature, these darkest objects become the universe's sharpest laboratory, testing the laws we trust most and exposing the seams where those laws don't quite agree. Because black holes aren't just astronomical curiosities. They're the one place where Einstein's gravity becomes so intense that quantum physics can no longer stay polite and separate. They force a collision between two theories that both work beautifully until they meet each other. And that collision raises questions that sound almost philosophical, but are rooted in real measurements. Can we photograph an object that cannot be seen? Can something be so dense that time itself slows to a crawl? And if a black hole can evaporate, what happens to everything that fell in every particle, every detail, every last bit of information? Stay with me, and you won't just collect amazing facts. You'll understand why we're listening to black holes, imaging their shadows, and using them to ask one of the boldest questions in all of science. What is reality really made of? Before we can ask black holes what reality is made of, we have to sit with a quieter question. How did something this extreme ever get admitted into serious physics at all, instead of being thrown out as a bad dream of the equations? If you wind time back to the early 20th century, there is no such thing as a black hole. There is only a new theory of gravity and a war. Einstein has just proposed that gravity is not a pull in the usual sense, but the bending of space and time themselves. This is already a shocking claim. Yet, in his own mind, the theory describes gentle things. Planets gliding on curved orbits, light bending a little as it passes a star, the universe as a whole, perhaps expanding or contracting very slowly. Nothing in his notebook suggests that he is secretly inventing cosmic traps from which not even light can escape. The first person to see that possibility is not Einstein. It is Karl Schwarzschild, a physicist serving on the Eastern Front. Between artillery barrages and the slow grind of a winter campaign, he works out an exact solution to Einstein's new equations. What space-time looks like outside a perfectly spherical, non-rotating mass. He sends the result to Einstein in a letter. On paper, the solution behaves in a strange way. If you squeeze a given mass inside a certain radius, the mathematics says light can no longer escape. There appears a surface beyond which all paths, even those of light, curve inward. Today, we would call this the event horizon. In that moment, it is just a peculiar feature of a formula derived under painfully idealized assumptions. A perfectly spherical star. No rotation. No magnetic fields. No messy astrophysics. Most people treat it as a curiosity. A kind of warning sign that you should not push the equations too far. After all, what does it even mean to say that light cannot escape? Where would it go? Does time stop? Does matter pile up at the center into a point of infinite density? The word singularity begins to appear in the literature, not as a physical claim, but as a label for where the mathematics seems to blow up. You can feel the discomfort under the technical language. Physicists like smooth, well-behaved functions. They like curves they can extend. This thing at the center of Schwarzschild's solution looks like a tear, a break in the story. For decades, the dominant attitude is simple. Nature will find a way around it. Real stars spin. Real matter is messy. Some new effect will surely intervene before the collapse becomes that extreme. Singularities are treated the way you might treat a pathological example in geometry. Interesting. Useful as a test case. But not something you expect to meet in the sky. It takes another war and another generation to change that. In the 1960s, Roger Penrose begins to attack the problem from a different angle. Instead of asking for perfect symmetry, He asks what gravity does to families of light rays when matter collapses under its own pull. He invents a new language of diagrams and global structure, and he proves something deeply unwelcome. Under very general conditions, if enough mass falls into a small enough region, you do not just get a strange coordinate artifact. You get an inevitable singularity, a place where the paths of particles and light simply end in finite time. The proof is technical, the conclusion is not. Einstein's theory, taken seriously, says that catastrophic collapse is not an optional extra. It is built into the logic of space-time itself. Notice where we still are in the story. There is no photograph. There is no X-ray source with a dramatic name. There is only a theorem that says, if you allow heavy enough stars to die, your universe must contain regions from which not even light can escape. And deep inside them, a place where the theory itself stops making sense. The reaction is mixed. Some people accept that the mathematics is solid, but hope that quantum effects will tame the singularity. Others remain uneasy with the whole picture. Yet slowly, almost reluctantly, the community begins to use a new phrase without quotation marks: black hole. Even then, these objects could still have turned out to be like dragons on medieval maps. Warnings at the edge of what is known. Useful as thought experiments. Never quite showing up in the data, the universe does not let us keep that distance for long. In the 1960s, new eyes are pointed at the sky in X-rays. Satellites begin to reveal a high-energy sky that is invisible from the ground. Among the first discoveries are bright, flickering sources that do not behave like normal stars. One of them sits in the constellation Cygnus. It becomes known as Cygnus X1. The light from this system is not the warm, steady glow of a star's surface. It is harsh and variable, as if something is rapidly heating and tearing at gas in a small region. Careful measurements show that the visible star in the pair is wobbling around, something invisible, something very massive and very compact. On January 7th, 1972, Louise Webster and Paul Murdin publish an analysis of the orbit. The unseen companion, they argue, is far too massive to be a white dwarf or a neutron star. Given what we know about how matter behaves under pressure, there is no stable object left in the catalogue. The simplest reading is that the invisible partner is a black hole. It is hard to overstate how disturbing that is, if you care about theories staying polite. For the first time, the universe seems to be pointing to one of the darkest corners of our mathematics and saying, that thing you hoped was just a trick of coordinates, I have actually built it. Not everyone is ready to accept that verdict. Stephen Hawking and Kip Thorne make a famous bet in the mid-1970s about whether Cygnus X1 is really a black hole. The terms are deliberately playful. The stakes are not. Hawking, ever the contrarian, bets that it is not. Privately, he seems to expect to lose. As he later explains, if observations prove it is a true black hole, he loses a wager but gains a universe that is as wild as the equations suggest. If it somehow is not, he wins some money, but physics loses a rare bridge between theory and reality. As more data arrive, the argument quietly shifts. There are still details to fight about, but the broad picture becomes harder and harder to avoid. Compact X-ray binaries like Cygnus X1 behave exactly the way you would expect if matter were spiraling into a deep gravitational well with a one-way surface. Gravity pulls gas off a companion star. The gas whirls around, heats up through friction, and radiates in X-rays before it crosses the horizon and disappears from our view. By the time Hawking concedes the bet, a strange reversal has happened. What began as an embarrassment of the theory has turned into one of its most robust predictions. Black holes move from the margins of speculation into the core of astrophysics. Textbooks list them alongside white dwarfs and neutron stars. Observatories are designed with them in mind. Whole careers are built on detecting their signatures. Underneath that professional routine, something else has shifted too. A certain kind of comfort has been taken away. It is one thing to treat singularities as signs a theory has been pushed beyond its domain. It is another to know that the universe is actively using that domain in the life cycles of real stars. The first fact, then, is simple and quietly unsettling. Black holes did not march into physics as obvious. Luminous objects, they crept in through a side door in the equations, were resisted as unphysical for decades, and only later revealed themselves in the sky. They forced us to accept that our best theory of gravity predicts not just gentle curves and slow orbits, but places where its own language runs out. Once you admit that, the next question is almost painfully direct. If nature really does build these objects, and if some stars end their lives by crossing that one-way boundary, what exactly has to happen to a star for it to be broken that far? The trail to that answer does not begin in silence. It begins in excess. With a star that is too big, too bright, and too impatient to last. Imagine a star tens of times heavier than the Sun, blazing in some crowded nursery of gas and dust. It lives in a kind of accelerated time, where a modest star like ours burns its fuel slowly over billions of years. This giant races through its life in just a few million. The price of shining that fiercely is that the star has to burn everything it has as fast as physics will allow. Inside, the star is not a ball of fire, but a kind of nuclear machine. Gravity pulls everything inward, trying to crush the gas. Nuclear fusion in the core pushes outward as light and high-energy particles try to escape. The star exists in a fragile truce between those two tendencies. The outward pressure from fusion keeps the star from collapsing. The inward pull of gravity keeps the fusion furnace dense and hot enough to keep going. For a while, that balance is stable. Hydrogen in the core fuses into helium, releasing energy. When hydrogen begins to run low in the center, the core contracts, heats up, and starts fusing helium into heavier elements: carbon, oxygen, neon, silicon. Each step up the periodic table requires higher temperatures and densities. The star builds an onion of burning shells, lighter elements fusing in the outer layers, heavier elements cooking in the deeper ones. If you could somehow pause time and look through the star's skin, you would not see a simple flame. You would see layers of nuclear reactions stacked on top of each other, each one a different way of temporarily holding back gravity. The core is like a kitchen where the menu keeps changing as the ingredients are used up. But there is a hard limit to what fusion can do. At some point, the core begins to assemble iron and nearby elements. And iron is where the trick fails. Fusing iron does not release energy. It costs energy. Instead of paying for pressure that can push back against gravity, the core is now spending energy just to build nuclei that do not help. The nuclear engine chokes. From that moment, the core's fate is sealed. With no new energy to support it, the inner region starts to collapse under its own weight. Gravity wins the argument. Not slowly, but catastrophically. As the core falls in on itself, the matter there is squeezed to densities far beyond anything we encounter on Earth. Atomic nuclei are jammed so close together that the electrons orbiting them have nowhere left to go. According to the Pauli exclusion principle, you cannot pack identical fermions particles like electrons into the same quantum state. When you try, an extra kind of pressure appears, a resistance that does not come from heat, but from the rules of identity in quantum mechanics. The collapsing core slams into that barrier. Electrons and protons are squeezed so tightly that many of them combine into neutrons, releasing a flood of neutrinos. In a fraction of a second, the star's central region transforms into something new, a ball of neutrons, only a few tens of kilometers across, yet containing more mass than the Sunday. If you scooped out a teaspoon of this stuff and somehow kept it intact, it would weigh as much as a mountain. This is a neutron star, held up not by thermal pressure from fusion, but by neutron degeneracy pressure, the same Pauli principle now applied to neutrons instead of electrons. For many massive stars, this is the endpoint. The outer layers crash inward, bounce off the suddenly rigid neutron core, and are hurled outward in a supernova explosion. For a brief moment, the dying star outshines the entire galaxy that hosts it. On February 23, 1987, lighter neutrinos from such an explosion reached Earth from the Large Magellanic Cloud, a small companion galaxy of the Milky Way. Astronomers named it Supernova 1987A. For a while, it became one of the most studied objects in the sky. Detectors underground recorded a burst of neutrinos, matching the idea that a collapsing core was turning into a neutron-rich object. Yet decades later, the exact nature of the remnant is still uncertain. Is there a neutron star hidden in the debris? Did the core continue collapsing further into a black hole? The universe has not given a clear answer. That ambiguity points to the next boundary in this story. Neutron degeneracy pressure can hold up a lot of mass, but not any amount. Squeeze too much material into the core, and even the neutrons run out of room in the available quantum states. The details depend on the physics of dense matter we still do not fully understand, but roughly speaking, if the core's mass is more than about 2 or 3 times that of the Sun, neutron pressure is no longer enough. At that point, the star is in trouble on a more fundamental level. There is no known stable form of matter that can withstand that much gravity while remaining in a conventional state. You can imagine more exotic possibilities: quark matter, strange stars, but beyond a certain mass. All of them seem to lead to the same conclusion in general relativity. Collapse does not stop. As the core shrinks, something remarkable happens in the geometry around it. There is a certain radius associated with a given mass in general relativity, a scale at which light cones the local maps of what can influence what tip inward so far that all future paths lead deeper into the object. This radius is often called the Schwarzschild radius in the simplest case. When the physical size of the collapsing core shrinks inside that radius, an event horizon forms. From the outside, this horizon is what defines a black hole. It is a boundary in space-time, not a material shell. Once the horizon exists, whatever crosses it cannot send signals back out. Light can still move locally at the usual speed, but the structure of space-time is such that all possible directions lead further in. The star has not fallen into something. By crossing that radius, it has become something new. Notice how quiet the recipe is, compared to how dramatic the result sounds. To build a black hole out of a star, you do not need exotic new physics. You need gravity, the known rules of quantum identity, and a star that is heavy enough that no known pressure can support its core once fusion fails. The event horizon is not an extra ingredient. It is the global, geometric outcome of allowing the collapse to finish. From the perspective of an observer far away, the process looks strangely slow. As the star's surface approaches the horizon, light climbing out from it is redshifted and delayed. Signals take longer and longer to reach you, and they arrive more and more stretched out in time. In that description, the star seems to freeze at the boundary, its image fading and dimming but never quite disappearing. From the perspective of matter falling in, the story is different. The infalling layers cross the horizon in a finite amount of their own proper time. They do not feel a hard surface at the horizon. There is no impact, no change in the local laws. Gravity may be intense, tidal stretching may be violent, but the horizon itself is locally unremarkable. The truly strange behavior of the equations is still ahead. In the region where curvature grows without bound, that double description, slow freezing from far away, swift crossing for those who fall, already hints at the way black holes will later force us to rethink what we mean by an event, by a moment, and by reality. But at this stage of the story, we can stay with a simpler truth. A massive star is a temporary truce. As long as nuclear fusion can generate enough pressure, the star can hold itself up against its own gravity. Once the fuel in the core is exhausted and the mass is high enough, the truce ends. First, gravity wins against ordinary gas pressure. Then it wins against electron degeneracy pressure. Then, if the core is heavy enough, it wins against neutron degeneracy pressure. The last failure is not just a physical accident, it is the gateway to a different kind of object. In that light, a black hole is not so much an external monster as the ultimate expression of what gravity does when there is nothing left to push back. It is what you get when a star has no more tricks. The physics that supported it, fusion, thermal pressure, quantum degeneracy, have all given way. The only thing left is space-time collapsing inward on itself. until it reaches a region where our description breaks. There is something quietly sobering in that. The same laws that let stars shine in the first place also contain, written between their lines, the possibility of their complete surrender. You do not have to add violence to the universe to get black holes. You only have to let its most massive stars live out their ordinary lives and then refuse to intervene when they die. From a human distance, this still feels abstract. These events play out over thousands or millions of years, in regions of space we will never visit. Yet when we point our instruments at certain supernova remnants, at violent X-ray sources, at flashes of neutrinos, we are catching glimpses of this process in different stages. We are watching gravity test the limits of matter, step by step, to see whether a given star will end as a neutron star or plunge through that last, invisible threshold. And once we accept that some stars really do cross it, that the universe truly manufactures event horizons out of ordinary stellar material, another question slowly appears. If the outside world loses access to whatever happens past that boundary, is the story really over there? Or is something still unfolding on the far side that our current theories cannot yet tell? To even ask that question, we have to loosen one of our deepest habits. The feeling that time is a single river flowing the same way for everyone, everywhere. Imagine two people with the same kind of wristwatch. Identical mechanisms, identical batteries, identical ticking. One stays on Earth, perhaps in a quiet laboratory near sea level. The other is carried upward, to an orbiting satellite. They both start their watches at the same moment, agree on a meeting time, and part ways. Years later, when the satellite clock is compared with the ground clock, they are not quite in step. The clock that spent its life higher up, in slightly weaker gravity and moving at high speed around Earth, has ticked at a different rate. The difference is tiny, but not optional. Engineers who work with the global positioning system have to correct for it every day. If they did not, the navigation in your phone would drift by kilometers in less than a day. Time, in other words, is not a universal background. It is part of the geometry of the universe. Near mass, near energy, near motion, time itself stretches and compresses. Einstein's way of saying this is that gravity is not really a force in the Newtonian sense. It is the curvature of space-time, the combined fabric of space and time. Objects follow the straightest possible paths in that curved geometry. What looks like a planet being pulled by an invisible force toward the sun is, in this picture, a planet following a straight line in a bent space-time. One of the most unsettling implications of that picture is that clocks are not sacred. A clock is just a physical system that counts some regular process, the swing of a pendulum, the vibration of a crystal, the transition of an electron between energy levels. If the geometry through which that system moves is distorted, the rhythm changes. A clock near a massive object really does tick more slowly than an identical clock far away. This is not an illusion created by signal delay. It is a difference in how much time elapses along each path through space-time. On Earth, this effect is small. The gravitational field is modest. You have to use very precise atomic clocks, and you have to wait to see the difference build up. But a black hole is gravity pushed toward an extreme. It turns a subtle correction into the main event. Picture an astronaut, call her A, equipped with a sturdy suit, a bright radio beacon, and a reliable clock. She hovers in a ship far from a black hole, floating in a region where space is almost flat, and time behaves almost like our usual intuition. Her friend B stays even farther away, in a safe orbit with a telescope and a receiver tuned to A's signals. At the beginning of the experiment, A and B compare clocks and agree on a plan. A will fire her thrusters briefly, turn off the engines, and fall freely toward the black hole. At regular intervals of her own wristwatch, say every few seconds, as she experiences them, she will send out a flash of light and a radio ping. B will record when those signals arrive and how their frequencies change. From A's point of view, the fall is surprisingly uneventful. Once the thrusters cut off, she drifts weightless. There is no sense of being pulled by a rope. If the black hole is huge, so that tidal forces are gentle over the scale of her body, she might feel almost nothing special as she approaches the horizon. Her clock ticks at its normal pace. Her heartbeat is regular. She sees the black hole's dark disk grow, the stars behind her distort into a ring and then a strange halo. But locally, the laws of physics around her seem the same. As she crosses the event horizon, she does not hit a wall. No alarm goes off on her instruments. The horizon is not a physical surface. It is a boundary in the map of what regions of space-time can send signals to which others. For A, that boundary is crossed in a finite amount of her own proper time. She keeps sending radio pings. Her clock keeps ticking. She may have only minutes or seconds left before tidal gravity becomes lethal. But those minutes are real for her. From B's point of view, nothing so casual is happening. As A begins to fall, B watches her clock on the video feed. At first, everything looks ordinary. The intervals between the flashes are regular. The radio pings arrive at a steady rate. But as A gets closer to the black hole, B begins to notice a change. The signals take longer and longer to arrive. The flashes become redder, their wavelength stretched by the struggle to climb out of the deepening gravitational well. Closer still, the effect becomes dramatic. The gap between pings grows. The image of A appears to slow, as if someone were gradually dragging the playback bar of a video toward a halt. The light from her suit is redshifted beyond visible wavelengths. Eventually, the signals are so delayed and so stretched that they fade into the background. From B's vantage point, A never quite crosses the event horizon. She simply seems to approach it more and more slowly, dimming and freezing near the edge. Two descriptions, two sets of events, both emerge from the same underlying geometry. A falls in and crosses the horizon in a finite time on her own clock. B never sees her cross, no matter how long B waits. In the language of relativity, both stories are valid. There is no absolute external time with respect to which we can declare one view to be the real one and the other to be an illusion. The event A crosses the horizon is, in a sense, partly hidden from B's universe. It happens inside a region from which no light can escape to reach B's eyes. This is one way in which black holes dismantle the idea of a single universal now. We are used to thinking that, at any given moment, the universe has a definite state. Here is what is happening right now on Earth. Here is what is happening right now on Mars. Here is what is happening right now near a distant star. But relativity teaches that right now is not a global concept. It depends on your motion and your position in space-time. A black hole pushes that lesson until it hurts. Mathematically, physicists learned to handle this by drawing new kinds of maps. Instead of using the familiar coordinates of space and time, they invented diagrams that compress an entire space-time into a manageable picture while keeping the paths of light rays at 45-degree angles. These are often called Penrose diagrams, after Roger Penrose, who used them to analyze the global structure of black holes and other solutions to Einstein's equations. On such a diagram, time does not run in a straight, familiar way. And space does not extend with simple Euclidean intuition. Instead, you see a diamond of sorts, representing the region outside the black hole, and a triangular wedge representing the interior. Lines that represent light move on fixed diagonals. Lines that represent the possible paths of physical objects tilt inside those bounds. In this compressed view, something striking becomes clear. The singularity inside a Schwarzschild black hole, the simplest, non-rotating kind, is not a point sitting in the middle, like a pebble at the center of a sphere. It is a space-like surface in the future, all time-like paths inside the horizon, all possible trajectories for particles that move slower than light, end on that surface in a finite proper time. Saying it more plainly, inside the black hole, moving forward in time inevitably carries you toward the singularity, in the same way that outside, moving forward in time carries you toward tomorrow. The singularity is less a place you fall into and more a moment in your personal future that you can no longer avoid once you are inside. That shift is subtle but important. In everyday language, we talk about the center of a black hole, as if you could in principle travel around it, or as if, with enough clever piloting, you might skirt its edge. The Penrose diagram says otherwise. Once you are within the horizon, the singularity lies ahead of you in time, not off to the side in space. Asking how to avoid it is like asking how to avoid Wednesday while walking steadily forward through a week. This is not just semantics. It tells us that the breakdown of the theory, what we call the singularity, is tied to the direction of time itself in that region. It is where general relativity stops being able to extend your world line further into the future. The strength of gravity there is so intense, the curvature of space-time so severe, that the equations cannot continue the story. From the outside, this interior future is forever hidden. No signal that encodes it can climb back out. When you look at a black hole from far away, even with the best telescopes we have built, you see only the edge behavior. You see the hot gas rushing around the horizon, the bending of light into a ring, the dim shadow where escaping paths are absent. You do not see time tipping over inside. In popular culture, this edge behavior was visualized with unusual care in the film Interstellar. The black hole Gargantua, designed with input from Kip Thorne, was shown as a dark sphere wrapped by a glowing lensed accretion disk. Light from the backside of the disk was bent around, so that you saw it as a halo above and below. The effect looked strange and theatrical, but it was grounded in real calculations. How light rays travel near a spinning black hole, how time dilates on the surface of a nearby planet, how gravitational redshift can stretch signals. When the film premiered on October 26, 2014, many viewers assumed that parts of it were exaggerated for drama. Yet when the Event Horizon Telescope team released the first real image of a black hole shadow in April of 2019, the resemblance was uncanny. A bright, asymmetric ring, a dark center, a visual proof that the geometry Einstein wrote down on paper had been built by nature around a real object. Behind that ring, time is still doing what the equations demand. Clocks closer to the horizon tick more slowly relative to clocks far away. Paths of light wrap, stall, or plunge inward. The present at the edge of the black hole is not the same for everyone. For matter circling near the horizon, the universe beyond looks sped up and blue-shifted. For observers far out, the infall looks slowed and reddened. Both are reading from the same curved script. When you let that sink in, a small everyday question becomes enormous. If time itself can stretch, slow, and tilt depending on where you are and how you move, what exactly are we referring to when we say now? The presence of black holes in the universe means that there is no single cosmic moment that all observers share. There are events that some can see and others can never see, no matter how long they wait. There are histories that are complete in one frame and forever unfinished in another. This is what it means, at a deeper level, to say that black holes trap not just objects but moments. They turn parts of space-time into regions that are causally sealed off. From outside, you can orbit, measure, infer, but you cannot participate in the interior's future. From inside, you cannot influence the outside world once you have crossed the horizon. The edge of a black hole is not just a location. It is a one-way cut in the network of cause and effect. Later, when we think about information, about whether anything that falls into a black hole is truly gone or somehow encoded on its surface, this bending and splitting of time will come back as the central puzzle. For now, it is enough to notice that the universe has allowed into existence regions where the very questions, what happened and when, no longer have single, shared answers. If the questions, what happened and when, can lose their universal meaning around a black hole, it is hard not to look backward and ask a different kind of question. How early in the universe's story did these distortions appear at all? We are used to thinking of black holes as the end states of stars. First galaxies form, then stars live and die, and only after that, in this comforting sequence, do black holes bloom at the centers of supernova remnants. In that picture, black holes are younger than almost everything else. They are late arrivals. But the universe has a habit of undermining our tidy chronologies. When astronomers look far away, they are looking back in time. The light from a distant quasar began its journey when the universe was much younger. Over the past few decades, surveys have uncovered quasars whose light set out when the cosmos was less than 1 billion years old. Yet, at their centers sit black holes with masses of hundreds of millions, even billions, of suns. Growing a black hole that large out of ordinary stellar collapses is not impossible, but it is demanding. You have to start with heavy seeds, feed them efficiently, and avoid blowing away the fuel with the very radiation that the feeding generates. You have to do all of this in a universe that is still assembling its first galaxies. This has led some physicists and cosmologists to a bolder thought. What if some black holes did not wait for the first stars at all? What if some of them were born in the very early universe, when everything was still hot and dense and there were no galaxies, no atoms, not even neutral hydrogen? These hypothetical objects are called primordial black holes. The word primordial here means exactly what it sounds like. Formed in the first fractions of a second after the Big Bang. Long before the processes that build ordinary stars have had time to act. To understand how that could even be possible, you have to visit the early universe in your mind. Shortly after the beginning, the universe is a hot, dense plasma of particles and radiation. Matter and light are so tightly coupled that you cannot have a beam of photons moving freely through space. Any attempt at travel is quickly interrupted by scattering. The universe is expanding and cooling, but on small scales it is almost perfectly smooth. Almost. When we measure the cosmic microwave background today, the faint, nearly uniform glow left over from when the universe was a few 100,000 years old, we see tiny ripples in its temperature. These ripples are tiny variations in density. Here, a region that was slightly overdense. There, a region slightly underdense. They are the seeds from which galaxies will eventually grow under gravity's patient pull. The amplitude of these fluctuations is small, roughly 1 part in 100,000. That is enough for structure to form over billions of years, but not nearly enough for everything to collapse immediately. If the early universe had been much lumpier, with regions significantly denser than their surroundings, some of those patches could have collapsed under their own gravity into black holes as soon as the expansion allowed it. In the standard cosmological picture, the measured smoothness of the cosmic microwave background strongly suggests that such extreme overdensities were rare or absent on the scales it probes. That already tells you something. The idea that primordial black holes make up all of the dark matter, or that they are abundant at many masses, is pushed into a corner by the data. But the cosmic microwave background is not sensitive to every scale. It mainly tells us about fluctuations on large, cosmological distances, corresponding to galaxy clusters and bigger. On much smaller scales, where tiny clumps would correspond to small black holes, the constraints are weaker. Cosmologists have taken advantage of that freedom to explore models in which, for a brief moment during the very early universe, some physical process enhances the power of fluctuations on those small scales. Perhaps during inflation, the rapid expansion phase thought to have stretched quantum fluctuations into cosmic seeds. The inflationary field briefly changed its behavior, allowing unusually large fluctuations at particular wavelengths. Perhaps defects in space-time, like cosmic strings, intersected and collapsed. Perhaps bubbles of a new phase of the vacuum formed and collided. All of these ideas are speculative. They are not built into the standard model of cosmology, but they are not pure fantasy either. They are mathematically consistent possibilities that we can, in principle, test. Each one creates a recipe for producing black holes in the first fraction of a second. When the density is enormous, the horizon scale is tiny, and even modest regions can contain enough mass to collapse. If such primordial black holes formed, they could span a vast range of masses. Some might be as light as mountains, others as heavy as stars, others still as heavy as the black holes we now see at the centers of galaxies. The exact distribution would depend on the details of the early fluctuation spectrum. Once formed, a primordial black hole does not care about its origin story. Gravity is indifferent. A black hole born from the collapse of a star, and a black hole born from an early universe overdensity of the same mass, would have the same external properties, the same gravitational pull, the same event horizon area, the same effect on surrounding matter. The only difference would be the story encoded in the pattern of their surroundings. This makes primordial black holes tricky to find. We cannot tag a particular black hole in the sky and say with certainty, this one is older than galaxies. Instead, we look for populations of compact objects and ask whether they could plausibly be remnants of the first moments. One method uses microlensing. If a compact mass passes between us and a background star or quasar, its gravity can act like a lens, temporarily brightening the background light. Surveys have monitored millions of stars in nearby galaxies and in the Milky Way's halo, looking for these telltale brightening events. The results show that there are not enough compact objects of certain masses to make up all of the dark matter. In particular, planetary and stellar mass primordial black holes cannot be the dominant form of unseen mass in our galaxy. Another approach looks at fragile structures like wide binary stars and thin stellar streams. If the halo were full of heavy compact objects, their gravitational tugs over billions of years would disrupt these delicate configurations. The fact that we still see such structures places limits on how many massive compact wanderers there can be. High-energy observations add more constraints. Very low-mass black holes would emit Hawking radiation strongly enough to be evaporating today. Their death throes could produce bursts of gamma rays. The observed gamma-ray background does not show the pattern expected if such evaporating primordial black holes were abundant. That closes off another large range of masses. In the last decade, gravitational wave astronomy has added a new kind of clue. The first black hole merger, detected by ground-based interferometers, involved two objects heavier than the typical black holes known from X-ray binaries. Their masses and the apparent abundance of similar events prompted some researchers to revive the primordial hypothesis. Perhaps these were not simply the corpses of massive stars, but members of a primordial population that had been quietly orbiting each other since the early universe. The debate is ongoing. Many astrophysicists argue that ordinary stellar evolution in low metallicity environments can produce black holes in the mass range we see. Others point out that the distribution of spins and masses in the detected mergers might carry subtle hints of a non-stellar origin for some fraction of them. For now, the safest statement is modest. Primordial black holes are not ruled out entirely, but they are strongly constrained. If they exist, they probably make up only a minority of the dark matter and inhabit particular, allowed mass windows. Even that modest possibility is conceptually striking. It means that somewhere in the universe there could be black holes that are not only older than any star, but older than the galaxies themselves. Objects that collapsed when the cosmos was still a hot fog of plasma, long before there were atoms, planets, or anything that could call itself life. If you let your mind rest on that image for a moment, something interesting happens. We often talk about ancient things on human scales: old trees, old buildings, old civilizations. In astronomy, we talk about old stars and old clusters. Primordial black holes, if they exist, would outdate all of that by an almost absurd factor. They would be more like scars in space-time, left over from the first violent moments, than like conventional astronomical objects. They would also be archives, in a certain indirect sense. Not archives we can open, but markers. Their abundance or absence, their mass distribution and spatial clustering would encode information about the physics of the early universe that we cannot probe in any laboratory. Just as the cosmic microwave background is a snapshot of the universe when it first became transparent, a population of primordial black holes would be a fossil record of how dense fluctuations behaved before that snapshot was taken. Here, the scientific and the existential gently overlap. The idea that the universe might contain relics from its first instance is already humbling. The idea that some of those relics are black holes, regions where time and space are so distorted that our best theories struggle to speak, adds another layer. It suggests that the tension between what we can describe and what we can only infer has been part of the cosmos from almost the beginning. In more familiar language, if primordial black holes exist, then black holes are not merely the end of certain stars. They are also, in some cases, among the universe's first durable structures. They sit at both ends of the cosmic timeline, as endpoints of stellar evolution and as possible direct products of the earliest physics we know how to imagine. Whether or not nature chose that path is still an open question. Future surveys, sharper microlensing campaigns, more detailed gravitational wave catalogues, and better maps of the gamma-ray sky will continue to tighten the net. Each non-detection, each new constraint, is also a kind of answer. It tells us that some imagined histories did not happen. But the fact that we can even ask whether some black holes might be older than galaxies tells you how far the concept has traveled. From a reluctant mathematical curiosity, to remnants of massive stars, to potential fossils from the very first fraction of a second, black holes have quietly claimed more and more of the cosmic timeline. And as they do, another reversal appears. What began as the darkest objects we could imagine start to look, in some ways, like beacons, not because they shine, but because their very existence, in different masses and eras, lights up otherwise hidden chapters of the universe's history. For something that hides light so completely, it is strange how often a black hole announces itself by making the sky flare. Imagine you are looking at an image from a deep survey. A single point lies far beyond the familiar scatter of nearby stars. It is so distant that, under the telescope, it shrinks to a dot. Yet this dot is brighter than the whole galaxy that hosts it. If you could hold an entire spiral of hundreds of billions of stars in one hand, this single, tiny point would still outshine it. For a while, astronomers did not know what to do with such objects. When the first of them appeared in radio surveys in the middle of the 20th century, they were classified as quasi-stellar radio sources. Radio points that looked like stars but did not behave like them. Their spectra showed broad, displaced lines, implying they were not nearby at all, but incredibly far away, in a universe that was much younger when their light began to travel. That distance created a problem. If these sources were as far away as the redshift suggested, then to look as bright as they did, they would have to be stupendously luminous. There is a kind of quiet horror in that calculation. You take the observed brightness, multiply it by the square of the distance, and discover that you are looking at something that radiates hundreds of times, or thousands of times, more energy than an entire normal galaxy. No known kind of stellar population can do that. You can pack young, massive stars together. You can ignite furious bursts of star formation. But there is a limit to how much light you can coax out of nuclear fusion spread across a disk of gas before you blow that gas away. These quasi-stellar objects were beyond that limit. The clue that finally made sense of them is simple and radical at once. Gravity can be a more efficient engine than fusion. When matter falls into a deep gravitational well, it gains kinetic energy. In the environment around a supermassive black hole, that energy does not simply vanish into the hole. Before crossing the horizon, the infalling gas collides with itself, spirals inward, and forms a disk. Friction and magnetic turbulence in that accretion disk heat the gas to enormous temperatures. The disk radiates, not gently, but violently, across the spectrum from radio waves to X-rays. A small fraction of the rest, mass energy of the gas, is enough to power the whole show. In nuclear fusion, only a small part of the mass of the fuel is converted into radiation. In an accretion disk around a black hole, a significantly larger fraction of the mass can be turned into heat and light before the remainder slips past the horizon. You could say, in a rough way, that gravity around a black hole can extract on the order of a tenth of the rest mass energy of matter and broadcast it, while ordinary stellar fusion manages much less than that over the star's lifetime. This is why a region not much larger than our solar system, wrapped around a supermassive black hole, can outshine a galaxy. It is not that the black hole glows, the hole itself remains dark. It is that matter, on its way to oblivion, is forced through the most extreme energy conversion funnel nature provides. Seen from across billions of light years, that funnel looks like a star that has forgotten its place. We call such objects quasars, and they mark the moments when young galaxies are feeding their central black holes at nearly the maximum sustainable rate. Closer to home, in cosmic terms, we have had the chance to look at one of these engines in much more detail. At the heart of the giant elliptical galaxy in the constellation Virgo, there is a black hole called M87 star. Its mass is on the order of billions of suns. Around it, a jet of particles and magnetic fields shoots out for thousands of light years, visible in radio waves, optical light, and X-rays. For decades, radio astronomers had been tracing its shape with networks of dishes scattered across continents, slowly sharpening the image of the jet's base. Then, in the second decade of the 21st century, an idea that had been maturing for a long time finally bore fruit. If you cannot build a single telescope the size of Earth, you can, in a sense, simulate one by synchronizing many distant radio dishes and combining their signals. This is the essence of very long baseline interferometry. The Event Horizon Telescope collaboration took that method to its logical extreme, linking observatories around the globe to create an Earth-sized lens tuned to the wavelengths where emission from the immediate surroundings of the horizon is brightest. For days, during a coordinated campaign, they stared at M87 star and recorded streams of data onto hard drives. Those drives were flown to central processing centers. Months of calibration and imaging algorithms followed. Slowly, out of the noise, a pattern emerged. On April 10, 2019, the collaboration released the result to the world, a blurry, uneven ring of radio emission surrounding a dark central patch. The brightness was not uniform. One side of the ring glowed more strongly, the imprint of gas orbiting at relativistic speeds and beaming its light toward us. But even in that first, soft image, two features were unmistakable: the crescent of light and the absence of light in the middle. That dark region is not the event horizon itself. It is larger, a sort of gravitational shadow, defined by photon orbits that skirt the black hole and by the ways light rays are bent and captured. Yet it is the first time we have directly seen, not just inferred, the silhouette of a black hole against its own luminous environment. People in the control rooms and conference halls where the image was first shown did not cheer in the way they might for a sports victory. Many of them went quiet. Some cried. There is something disorienting about watching an idea that has lived for more than a century as lines in equations and simulations suddenly manifest as a ring of real light on a screen. After that first image, other instruments joined the conversation. The James Webb Space Telescope, with its infrared eyes, has observed M87 star and its jets, adding detail about how dust and gas move and glow in the regions further out from the horizon. X-ray observatories map the hotter, more rarefied plasma. Together, these views show a system in which a black hole is not a passive drain, but an active participant in galactic life. The jet from M87 star carries an enormous amount of energy out into the surrounding gas. As it plows through the intergalactic medium, it inflates bubbles, drives shocks, and stirs turbulence. This feedback can shut down or regulate star formation by heating the gas that would otherwise cool and condense into new stars. So the same object that, on small scales, is shredding and devouring matter, on larger scales, is shaping the fate of its host galaxy. It lights up the sky as a quasar when fuel is abundant. It sculpts the environment with jets and winds. It may even decide, indirectly, how many generations of stars the galaxy will be able to form. In that sense, the word monster, often used in popular descriptions of black holes, is both apt and misleading. Apt, because the energies and scales involved are far beyond anything our intuition was built for. Misleading, because we tend to imagine monsters as intruders, as things that do not belong. Supermassive black holes are not intruders. They are woven into the history of galaxies. We now think that almost every large galaxy hosts one at its center, and that the growth of the galaxy and the growth of its central black hole are entangled. This is another way in which black holes dismantle a comfortable picture. We might like to think of galaxies as being powered by their stars, with black holes as dangerous but secondary. Instead, Observations keep telling us that in certain phases of a galaxy's life, the dominant beacon is the accretion flow onto the central black hole. In others, even when the nucleus is quiet, the past activity of that black hole has left cavities, ripples, and temperature patterns in the surrounding gas that still govern what can happen next. The paradox, if you want to call it that, is simple. The most efficient engines of light and radiation in the universe are built around objects from which light cannot escape. The darkness at the center is precisely what allows such a deep gravitational well. And that well is what makes it possible to convert in falling mass into radiation with such ruthless efficiency. If you step back and look at a catalogue of known quasars, each dot on that list is not just a curiosity. It is a statement that, in that galaxy, at that epoch, the central black hole found enough fuel to burn on the edge of its horizon and shout across cosmological distances. When we tune radio dishes, X-ray telescopes, and space observatories to these sources, we are effectively listening to matter losing the final argument with gravity, and, in the process, lighting up the universe for us. It is easy, standing on a small planet, to think of stars as the natural units of light. They are what we see with our eyes. They set our cycles and seasons. Yet on the largest scales, the brightest things are often not stars at all, but the side effects of matter spiraling into absence. There is a quietly unsettling sentence that follows from this. The universe's most brilliant lighthouses are lit not by creation, but by surrender. The beacons that guide our telescopes to the edges of the observable cosmos are powered by gas, dust, and stars stretching, heating, and finally disappearing beyond horizons we cannot look past. Put more plainly, the brightest lights out there are on the very doors where the visible story ends. The strange part is that you do not have to look to distant quasars to find such a door. One of them sits in the story you grew up with, woven into the familiar band of the Milky Way that crosses the night sky. If you go somewhere truly dark, away from city lights, and let your eyes adjust, the Milky Way appears as a pale river overhead. It looks delicate, almost fragile, as if a touch could smear it. But that river is a disk of hundreds of billions of stars, gas clouds, and dark matter, all wheeling around a common center. Near that center, hidden behind thick curtains of dust, sits a supermassive black hole. Astronomers call it Sagittarius A star. The name sounds like a catalog entry, but the object itself is anything but modest. Its mass is a few million times that of the Sunday. If you could somehow replace the Sun with Sagittarius A star and keep the planets where they are, Earth would complete its orbit in a matter of hours. Yet, all of that mass is confined to a region smaller than the orbit of Mercury. We cannot see Sagittarius A star in ordinary light because the dust between us and the galactic center is too thick. Visible photons are scattered and absorbed long before they reach Earth. The first hints of something unusual there came from radio observations in the middle of the 20th century. A compact, bright radio source sat very near the dynamical center of the Milky Way, in the direction of the constellation Sagittarius. Something energetic and confined was happening there. Radio waves were not enough to weigh it. For that, astronomers needed to see the motions of stars orbiting in its immediate neighborhood. That meant going into the infrared, where dust is more transparent, and building instruments that could track the positions and velocities of individual stars near the galactic center with exquisite precision over many years. Two groups, one based in Europe and one in the United States, took on that task. They pointed large telescopes equipped with adaptive optics toward the same crowded patch of sky, night after night, season after season. What looked, at first glance, like an indistinct blur of light slowly resolved into dozens of individual stars, each with its own path. One of them, now famous, is called S2. It follows a long, narrow orbit that carries it close to the unseen center and then flings it far out again. The full circuit takes about 16 years. On one of its closest approaches, S2 comes within a distance that is only a little larger than the size of our own solar system, and it moves at a few % of the speed of light. By mapping that orbit and others, and by fitting them with the equations of gravity, the teams could infer the mass of the central object they were all circling. The answer that emerged was stark. Several million solar masses were concentrated in a region so small that no cluster of ordinary stars or dark stellar remnants could be stable there for long. The only plausible explanation left was a supermassive black hole. This was not a single eureka night. It was a conclusion distilled from decades of patient work, connecting dots on images and following them as they curved, sped up, and slowed down under an invisible pull. When the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics on October 6, 2020, half of it went to Reinhard Genzel and Andrea Ghez for this very achievement, demonstrating that the center of our galaxy hosts a supermassive compact object best described as a black hole. The other half went to Roger Penrose for the theoretical work that had shown such black holes are not exotic misbehaviors, but natural predictions of general relativity. By then, Sagittarius A star was already a central character in galactic astronomy. Models of the Milky Way's structure anchor the coordinate system on it. Maps of gas flows, star formation, and spiral arm dynamics all include its mass as a key parameter. It is less a monster lurking under the bed than a weight placed carefully at the middle of a spinning disk, keeping the system coherent. Yet its everyday behavior is surprisingly quiet. Sagittarius A star is not, at present, a quasar. It is underfed. A trickle of gas drifts toward it, occasionally flaring when clumps are heated and accelerated. But most of the time, it is faint. If you could evacuate the dust and look directly toward the galactic center with sensitive X-ray and radio eyes, you would see sporadic flickers, not a continuous blaze. That quietness made the next step both more difficult and more intriguing. After the success with M87 star, the Event Horizon Telescope collaboration turned their global array towards Sagittarius A star. The goal was similar: to resolve the immediate surroundings of the horizon and, if possible, see the shadow cast by the black hole against the emission of the hot, swirling plasma around it. Sagittarius, a star, presented new challenges. Because it is much closer to Earth than M87 star, its apparent size on the sky is comparable, but the gas around it completes orbits in minutes, not days. The source is intrinsically variable on timescales similar to the observing time. Imaging something that changes while you are looking at it is much harder than imaging a slowly rotating, effectively steady ring. The team dealt with this by combining data from many observing nights and many theoretical models. They generated libraries of possible accretion flows that matched our understanding of plasma physics near a black hole. They simulated how these flows would appear to the telescope, then compared the simulations to the actual data. Gradually, they constrained the possibilities enough to extract a common shape. On May 12, 2022, they released the first image of Sagittarius A star to the public. It showed, once again, a ring-like structure of emissions surrounding a darker central region. The ring was blurrier and more mottled than the one around M87 star, a reflection of the rapid variability and the different observing conditions. But its size and overall geometry were exactly what general relativity predicts for a black hole of the mass inferred from stellar orbits. Seeing that alignment between two completely different methods is a quiet triumph. On the one hand, you have the dance of stars, measured in infrared light, tracing the gravitational field over decades. On the other, you have the lumpy glow of hot gas mapped in radio waves, probing the strong field regime just above the horizon. Both stories point to the same invisible anchor. It is worth pausing on what that means. The dark heart of our galaxy is not an abstract solution to Einstein's equations. It is a specific object with a measured mass, a set of observed flares, a catalogue of orbiting stars, and now an image of its own shadow. It has a position in the sky you can point at. It has a history in the data archives. When you step outside at night and see the Milky Way, you are looking at a disk of stars that all, in a very literal sense, are part of a long, slow orbit around that object. The Sun, too, is on such a path. Our solar system is currently tens of thousands of light years from the center, taking hundreds of millions of years to complete a single circuit. We are far enough that local gravity from nearby stars dominates our immediate environment. But the overall shape of our orbit is set by the combined mass of the galaxy, including the contribution from Sagittarius A star. Sometimes, stars do not keep their respectful distance. If a star or a gas cloud wanders too close to the central black hole, tidal forces can tear it apart. The difference in gravitational pull between the near and far sides of the object stretches it, distorts it, and eventually shreds it into a stream of debris that wraps around the hole. As that debris spirals in, it heats up and produces a flare of radiation. These events, called tidal disruption events, have been observed in other galaxies. In the future, with more sensitive monitoring, we may catch such a catastrophe in our own. Thinking about all of this, there is an odd intimacy in the fact that our home galaxy has such a core. For most of human history, the Milky Way was a mythic river or a road of spirits. Today, it is a flattened system of stars orbiting a center we cannot see with our eyes. At that center sits a region where time slows, light bends, and our equations edge toward their limits. It does not threaten us in any practical way. The black hole is too far. Its tidal influence at our distance is negligible. No realistic scenario has it suddenly swallowing the outer parts of the galaxy. Its main role in our lives is gravitational and symbolic. Gravitational, because it helps shape the galaxy we inhabit. Symbolic, because it is a reminder that the exotic physics we discuss in abstract terms is not confined to faraway quasars and simulations. It is part of the structure of home. The monster at the center of the Milky Way, then, is neither a devourer waiting in the dark, nor a mere footnote to stellar life. It is a structural feature of our galaxy, a massive, silent presence around which stars trace their long orbits and gas clouds feel their way. It has a name, a mass measured from orbits, a photograph of its shadow, and a story written across many decades of human observation. The moment you know there is a black hole at the center of your own galaxy, another thought slips in almost automatically. If gravity can curve space and slow time, can it also make the universe ring? Einstein's equations say yes. Not loudly, not with fanfare, but tucked into the mathematics is a simple consequence. If you disturb space-time with moving masses, especially compact ones in tight orbits, the disturbance does not just sit there. It propagates outward as waves. Not sound waves in air, not light waves in a field. Ripples in the geometry itself. He wrote about these ripples in the second decade of the 20th century, then spent years worrying about whether they were real or an artifact of his chosen coordinates. For a while, he even convinced himself they might not exist in a physical sense. The equations were subtle. The interpretation was not obvious. Eventually, after arguments and corrections, the consensus settled. Gravitational waves are as real as the theory that predicts them. Real, but almost impossibly faint. By the time waves from distant systems reach Earth, the stretching and squeezing of space they cause is so small that you can describe it only by saying things like, the distance between two objects 4 kilometers apart changes by less than the width of a proton. The Earth's crust moves more than that when a truck rolls by. Thermal noise in the atoms of your measuring device is larger than that. For most of the 20th century, the idea of actually detecting such tiny distortions felt like a kind of heroic fantasy. And yet, quietly, humans started building ears. In laboratories and fields, physicists constructed instruments that did not look like telescopes at all. They looked like long, evacuated tunnels, arranged in an L shape, with mirrors hanging at the ends and lasers bouncing back and forth between them. The basic idea was simple in principle. If a gravitational wave passes through, it will make one arm slightly longer and the other slightly shorter, then swap, rocking the distances at a rhythm set by the source. The paths of the laser beams will lengthen and shorten accordingly, creating a telltale interference pattern when they recombine. Turning that principle into a working observatory took decades. You have to isolate the mirrors from vibrations, from seismic noise, from trucks and wind and distant storms. You have to control the laser's stability to absurd precision. You have to monitor and model every known source of disturbance, so that if something strange appears, you can be confident it is not just a glitch. In the 1970s and 1980s, early prototypes proved the method was viable. In the 1990s, construction began on the first large-scale observatories in the United States. One in Washington State and one in Louisiana. Together, they became the Laser Interferometer Gravitational Wave Observatory, usually shortened to LIGO. Similar projects grew in Europe and later in Japan. For years, the detectors listened and heard nothing beyond noise. This was not a failure. It was a way of learning the language of the instrument itself. Every time a storm rolled in, the data twitched in a certain way. Every time a piece of equipment misbehaved, another pattern appeared. The teams learned to spot and catalog these artifacts. They upgraded mirrors and lasers. They refined suspension systems. Slowly, the sensitivity improved. By the middle of the second decade of the 2000s, advanced versions of the detectors were coming online, capable, in theory, of hearing mergers of black holes and neutron stars across hundreds of millions, even billions, of light years. No one knew when the first real signal would arrive. There was even a plan to inject fake signals, secretly, into the data stream to test the collaboration's ability to find and analyze them. In the morning hours of a day in September, in the year 2015, a characteristic pattern appeared in the data at both LIGO sites. It lasted less than a second. If you compressed the waveform into the range of human hearing and played it back through a speaker, it sounded like a short, rising chirp, a lower tone quickly sweeping up to a higher tone and then cutting off. On the screen, the chirp was a curve. Its frequency and amplitude increased together in a way that matched years of numerical simulations of two massive black holes, spiraling inward, losing orbital energy to gravitational radiation, and then finally plunging together to form a single, larger black hole that rang down like a bell. The masses implied by the signal were surprising. Each of the initial black holes was roughly a few tens of times the mass of the Sunday. Their merger released, in that brief fraction of a second, an amount of energy in gravitational waves equivalent to several suns' worth of rest mass. For that instant, the system outshone all the stars in the observable universe in gravitational wave luminosity. Yet by the time those waves washed through Earth and rattled the mirrors in the LIGO arms, the effect on the arm lengths was smaller than the width of an atomic nucleus. Inside the collaboration, the mood was a mixture of excitement and suspicion. This could be it. It could also be a test injection carried out by a small blind injection team or an undiagnosed instrumental artifact. The next months were not a victory lap, but a long audit. Teams went through the hardware logs, checked for any indication of test signals, and looked for coincident disturbances. They independently analyzed the data with different pipelines, different assumptions, different noise models. They cross-checked with other observatories. At some point, the blind injection team revealed that they had not, in fact, planted any signal. The candidate stood. On February 11, 2016, the discovery was announced to the public. The press conference included a simple audio clip. The rising chirp. It is hard to convey what a conceptual shift that little sound represented. For the first time, we were not just seeing the universe in light, or inferring it from gravitational pulls, but listening to space-time itself vibrate under the strain of colliding black holes. The event received the kind of attention reserved for true turning points. 2 years later, the Nobel Prize in Physics was awarded in part for the decisive contributions that made the detection possible. But the deeper change was quieter. An entirely new sense had been added to astronomy. With light, you mostly see surfaces and gas. Stars, disks, jets, glowing clouds, dust lanes. With gravitational waves, you are sensitive to motion in the deep interior of systems. The orbits of compact objects, the final moments of inspiral and merger, the shape of the space-time funnel itself. Light is easily absorbed, scattered, or blocked by dust. Gravitational waves pass almost unhindered through matter. After the first black hole merger, more signals followed. Pairs of black holes of various masses. In one particularly rich case, a pair of neutron stars spiraled together and merged, producing not only gravitational waves, but also a burst of gamma rays and an optical afterglow. Telescopes around the world slewed to the patch of sky indicated by the wave data. They saw a transient source that faded over days, its light changing color in a way that matched predictions for radioactive elements being forged in the merger debris. That event tied together three things at once: the existence of gravitational waves, the violent fates of neutron star binaries, and the origin of some of the heavy elements in the periodic table, such as gold and platinum. Pieces of jewelry and electronic components on Earth are made partly of atoms that were likely assembled in cosmic collisions, whose space-time echoes we can now, in principle, hear. There is an odd humility in how the first detection looked in the raw data. No majestic picture, no colored nebula, just a slightly wiggly line on a screen, a tiny excess above a noisy background, the kind of thing you might miss if you were not looking for exactly that pattern. And yet behind that wiggle was a story. Two invisible black holes, in a distant galaxy we cannot see, orbiting each other many times per second as they shrink their orbit and finally collide. This is what it means to say we listened to black holes before we saw them. Long before the Event Horizon Telescope gave us ring-like images of horizons, the universe had already been sending us their merger songs. We simply did not have ears sensitive enough to hear them. Now that we do, the sky has acquired a new kind of weather. Somewhere, as you read this, there are compact binaries tightening their orbits, neutron stars tidally distorting each other, black holes whirling. Their gravitational waves are passing through you, through Earth, through the sun, stretching and squeezing space by imperceptible amounts. We are embedded in a faint, continuous chorus of distant catastrophes. For most purposes of daily life, that chorus is irrelevant. It does not knock pictures from walls or sway buildings, but intellectually, it changes the posture with which we look up. When you see a photograph of a black hole's shadow, you can now imagine not only its silhouette, but also its potential voice. When you think about binary stars in a dense cluster, you can imagine their quiet, spiraling duet leaking energy into space-time as waves. There is also a deeper echo in all of this. General relativity, when first proposed, was a purely theoretical construction tested on subtle shifts in Mercury's orbit and tiny deflections of starlight during eclipses. Gravitational waves were once the most ethereal of its predictions, debated on blackboards and in letters. A century later, those waves are part of our observational toolkit. Black holes, once mathematical curiosities, are both the sources and the subjects of this new astronomy. In a sense, every successful detection is an admission. We are acknowledging that the universe is not just a place where light moves through a fixed stage, but a place where the stage itself can shake, sing, and carry information. And the instruments doing this work are not sitting calmly in space with a clear view. They are built on a seismically noisy planet, by beings who only recently learned that their own galaxy has a dark heart. The most striking part may be this. To hear black holes collide, you do not need to travel to them. You do not even need to see their host galaxies. You need mirrors, lasers, patience, and a theory that tells you what kind of pattern to listen for in the fluctuations of distance between hanging masses. Out of that almost absurd delicacy comes a new way of knowing that these invisible, heavy, time-bending objects are out there, meeting, merging, and ringing long after the light of their births has faded. It would be tempting to stop there, satisfied that we have heard black holes collide and seen their shadows, and to let them remain as perfectly dark, perfectly silent endpoints. But quantum physics is stubborn, and it does not allow anything to be that absolute. In the classical picture of general relativity, a black hole is flawless in its simplicity. Once it settles down, it is fully described by only a few macroscopic parameters: its mass, its spin, and its electric charge, which in astrophysical contexts is usually negligible. No hair, as the slogan goes. Nothing ever comes out. Anything that falls in is gone to the outside world, its detailed structure erased. Only its contribution to the total mass and spin remaining legible at the horizon. Quantum field theory, which governs the behavior of particles and fields on small scales, is not comfortable with such clean, one-way boundaries. It brings with it a different intuition about emptiness. In quantum terms, the vacuum is not an inert void. It is a restless state in which fields fluctuate, in which pairs of particles and antiparticles can momentarily appear and annihilate, as long as the borrowing of energy is repaid quickly enough to respect the uncertainty principle. When Stephen Hawking began to think seriously about black holes in the 1970s, he did not set out to overthrow their perfect darkness. He wanted to understand something technical: how quantum fields behave in the curved space-time outside a horizon. He had previously argued, along with others, that nothing could escape from within a black hole without violating classical causality. In that mindset, the horizon was a strict divider between the inside and the outside. What he found, after months of calculation, was the opposite of what he expected. When you treat quantum fields properly in the space-time of a black hole, the state that looks like empty vacuum far away is not empty near the horizon. To a distant observer, the black hole appears to emit a steady flux of particles with a thermal spectrum, as if it had a temperature. The temperature is not arbitrary. It is inversely proportional to the mass of the black hole. Very small black holes, if they could exist, would be extremely hot, radiating strongly. Stellar mass black holes are much cooler, their temperature far below that of the cosmic microwave background. Supermassive black holes, like the one in the center of the Milky Way, are almost unimaginably cold. On March 1, 1974, Hawking's paper with the deliberately provocative title "Black Hole Explosions" was received by the journal Nature. In it, he laid out the argument that black holes must emit thermal radiation and therefore must lose mass over time. If a black hole radiates energy to infinity, and if the only reservoir of mass energy it has is its own mass, then slowly, almost imperceptibly, it must shrink. This was a conceptual earthquake. A black hole, in the classical sense, is unchanging unless you throw matter or radiation into it. In the quantum-corrected picture, even an isolated black hole sitting in an otherwise empty universe will evolve. It will emit Hawking radiation, lose mass, and, given enough time, evaporate completely. The popular image that grew up around this idea involves virtual particle pairs forming near the horizon. One member of the pair falls in, the other escapes to infinity. The escaping particle becomes part of the Hawking radiation, while the infalling one carries negative energy relative to the outside, reducing the mass of the black hole. This story is a metaphor, and like all metaphors in physics, it both helps and misleads. The precise derivation of Hawking radiation does not require literal little billiard balls popping into existence at the edge and deciding which way to go. It is about how quantum fields, which have infinitely many degrees of freedom, respond to the curved background geometry. It is about modes that are seen as vacuum by one observer and as particles by another. But the metaphor captures one crucial point. The radiation is not coming from deep inside the hole. It is generated in the region just outside the horizon, where quantum fluctuations are stirred by the gravitational field. In that sense, the black hole is less a glowing lump of material and more a boundary condition that changes what empty space means nearby. For ordinary astrophysical black holes, this effect is fantastically weak. A stellar mass black hole has a temperature of a tiny fraction of a degree above absolute zero, far colder than the cosmic background. It is absorbing more energy from the bath of photons around it than it is emitting as Hawking radiation. It will not start to truly evaporate until the universe has expanded and cooled much more, to temperatures far below anything we can currently imagine in practice. The timescales involved are equally extreme. The evaporation time for a black hole with the mass of the Sun, in an otherwise empty universe, is far longer than the current age of the cosmos, by an absurd factor. For a supermassive black hole, the evaporation time is longer still. So much so that ordinary language struggles to give a sense of it. Hawking knew this. He was not suggesting that the black holes in today's galaxies are about to vanish in a puff of high-energy photons. The importance of the result was not practical in that narrow sense. It was conceptual. It told us that black holes are thermodynamic objects. They have a temperature. If they have a temperature, they have an entropy. And if they have an entropy, we can begin to ask what microscopic degrees of freedom that entropy is counting. Jacob Bekenstein had already taken a step in that direction. He had argued, on more general grounds, that the area of a black hole's event horizon behaves like an entropy. It never decreases in classical processes, and when matter with entropy falls in, the increase in horizon area can be interpreted as compensating for that loss. He proposed that the entropy of a black hole is proportional to its horizon area, measured in units of the Planck length squared. Hawking's calculation fixed the constant of proportionality to make the first law of thermodynamics hold for black holes, to relate changes in mass, area, and angular momentum in a way analogous to energy, entropy, and work. He found that the entropy must be 1/4 of the horizon area in Planck units. Put differently, a black hole has an entropy equal to the area of its horizon divided by 4 times the square of the Planck length. The numbers are staggering. A black hole with the mass of the Sun has an entropy far greater than the entropy of all the ordinary matter inside the Sun before it collapsed. A supermassive black hole's entropy dwarfs that of the stars in its host galaxy. In terms of raw counting of microstates, black holes are the most entropic, most information-rich objects we know how to describe. Here again, what began as a question about whether a black hole can radiate leads to something broader. If the entropy is proportional to area, not volume, then the information content of a region might scale with its boundary, not its interior. That thought will open a door in the next chapter toward holography. But it begins here, with the realization that a supposedly perfectly black object must in fact glow with a faint thermal halo. There is another layer to Hawking's story that is more personal and, in a sense, more human. At first, he did not believe the result. It seemed to contradict his own earlier assumptions. He spent time trying to find the flaw in the calculation. Only when he failed to do so did he accept that the equations were telling him something he had not expected. He later joked that his discovery was that black holes are not black. Once you take that seriously, you cannot help but think about smaller black holes. If any exist, a primordial black hole with a mass comparable to a mountain would have a much higher temperature than a stellar mass black hole. It would radiate strongly in gamma rays and other high-energy photons. Its lifetime would be shorter, perhaps comparable to or less than the current age of the universe. The very lightest primordial black holes, if they were born at all, would have already evaporated, ending in a final, brief burst. Physicists have searched for signs of such explosions in the gamma-ray sky. So far, there is no clear evidence that they are common. That lack of evidence constrains how many small primordial black holes there could be. It is another way in which Hawking's thought experiment, carried out on paper, reaches out into observational astronomy. On the largest timescales, Hawking radiation also gives us a kind of distant, speculative epilogue to the cosmic story. Imagine a universe in which matter continues to cluster and form galaxies for a while. Then star formation slows as gas is used up. Stars age, die, and leave behind white dwarfs, neutron stars, and black holes. Over unimaginably long periods, gravitational encounters and rare collisions feed the black holes, which then merge, leaving a smaller number of more massive ones scattered through the darkening universe. When all the other fuel is gone, when normal matter is either locked into diffuse debris or black holes, the only luminous processes left are the whispers of Hawking radiation. The universe would slowly fill with a thin, cold bath of photons and other particles leaking from evaporating horizons. Eventually, even the largest black holes would dwindle and vanish. To call this an ending is both natural and misleading. On the one hand, it is a narrative. Structures form, evolve, and dissolve. On the other hand, Hawking radiation is not an end in the sense of a dramatic final act. It is a gentle, extremely slow fade, driven by quantum fluctuations at the edge of what used to be the darkest objects in existence. There is a quiet irony in all of this. The thing that makes black holes so terrifying in classical general relativity, their absolute refusal to let anything out, is precisely what quantum physics refuses to tolerate. Instead, It replaces absolute silence with a nearly inaudible hiss, a thermal murmur that, over extreme spans of time, erodes the horizon. If you zoom out even further, you can see a pattern in how our understanding has shifted. First, black holes were unphysical singularities to be avoided. Then they became real astrophysical objects that swallow light and matter but do not give anything back. Then they became sources of gravitational waves, ringing the universe when they collide. And with Hawking's insight, they became thermodynamic systems that radiate, lose mass, and eventually disappear. Each step moves them a little further away from the role of final, absolute endpoint. Each step introduces more dialogue between inside and outside, between geometry and quantum fields, between what falls in and what, somehow, later emerges. And each step makes the question, what happens to information in a universe with black holes, more urgent and more difficult to ignore. The moment you accept that black holes have a temperature and can evaporate, a quieter, more uncomfortable question creeps in behind it. If they can radiate away, what happens to the details of everything that ever fell in? In everyday life, we are surrounded by processes that seem to erase detail, but do not quite. Burn a book, and the letters are gone from the page. But in principle, the information is still scrambled in the smoke, the ash, the pattern of heat in the air. Mix cream into coffee, and you cannot unmix it. But the microscopic positions and velocities of the molecules still remember what happened. The equations of quantum mechanics insist on this. They say that the evolution of a closed system is unitary, which is a precise way of saying that information is never truly lost, only rearranged. Classical black holes look like an exception. Throw in a diamond, a library, and an astronaut. And from the outside, you are left with a slightly heavier, slightly more spinning hole. If, on top of that, Hawking radiation is exactly thermal, then when the hole finally evaporates, you are left with a cloud of featureless heat. The rich, specific quantum state that went in seems to have been replaced by something that remembers only a few coarse parameters. This is the black hole information problem, and it is where the strange geometry of horizons meets the bookkeeping of quantum theory. If information really disappears, quantum mechanics is wrong or incomplete in a deep way. If it does not disappear, then our naive picture of evaporation must be missing something. The area law for black hole entropy gives a hint of an answer and deepens the puzzle at the same time. In ordinary systems, the maximum amount of information you can store usually scales with volume. A gas in a box, a memory device, a piece of matter. Double the size, and you roughly double the number of microscopic configurations available. The interior is what matters. For a black hole, the entropy scales instead with the area of the event horizon. Double the radius, and the area, and hence the entropy, grows with the square of that change. The interior volume, which in some coordinate choices can be made enormous, does not appear directly in the formula. Jacob Bekenstein, thinking along these lines, proposed something bold. Perhaps the black hole is not the only system with such a bound. Perhaps there is a fundamental upper limit to how much information can be packed into any region of space. And that limit is proportional not to the region's volume, but to the area of its boundary, measured in units set by the Planck length. This idea is often called the Bekenstein bound. Imagine a spherical region floating in otherwise empty space. You can fill it with matter, heat it up, compress it, encode messages in the arrangement of particles. If you try to push too much information into that region, you eventually reach a point where adding more makes it gravitationally collapse into a black hole. At that moment, the entropy is given by the area of the horizon. If you had somehow managed to store more than that before collapse, you would violate the second law of thermodynamics, because the entropy of the resulting hole would be smaller than the entropy of the matter that formed it. So the black hole does not just hide information. It seems to set the maximum information capacity of the region it occupies. The ultimate hard drive is not a dense crystal or an advanced memory chip. It is a horizon. Thinking this way leads Gerard Hooft and Leonard Susskind in the 1990s to a radical proposal, now known as the holographic principle. If the maximum information in a region is proportional to its surface area, then it might be more natural to think of the true degrees of freedom as living on that boundary. The three-dimensional world we experience could, in some deep sense, be like a hologram, a projection of information encoded on a lower dimensional surface. This is not meant in the trivial sense of a simulated universe running on a computer in some other reality. It is a structural statement about how gravity and quantum field theory might fit together. The physics inside a region could be fully described by a theory without gravity living on its boundary, with one fewer dimension. The black hole entropy formula becomes a clue that space-time itself might be emergent from something more abstract. For a while, this was just a tantalizing principle. Then, in the late 1990s, Juan Maldacena wrote down a concrete example. He proposed that a certain kind of gravity theory in a space with constant negative curvature, anti-de Sitter space, could be exactly equivalent to a conformal field theory without gravity living on the boundary of that space. Two very different-looking theories, one with black holes and curved geometry, one with particles and fields on a flat boundary, turned out to be two descriptions of the same underlying physics. This correspondence, often called the anti-de Sitter/conformal field theory duality, is technically specific. Our universe is not anti-de Sitter. Its large-scale geometry is different. The field theory involved is highly symmetrical and unlike the messy mix of forces and particles we see in the laboratory. But as a proof of concept, it is astonishing. It says, in a carefully defined context, that everything happening in a volume of space with gravity can be rephrased as information living on a lower dimensional surface with no gravity at all. In that framework, a black hole in the bulk space corresponds to a thermal state in the boundary field theory. The Hawking radiation and the apparent loss of information are reinterpreted as perfectly unitary evolution in the boundary description. Nothing is lost. It is just encoded in a highly scrambled way in the degrees of freedom on the boundary. If you take this seriously, the statement that a black hole's information fits on its surface becomes more than a metaphor. The two-dimensional horizon area, measured in tiny Planck-sized patches, really does count the number of possible internal configurations. Each patch corresponds, very roughly, to a bit of information. Everything that happened during the formation of the hole, every nuance of what fell in, is reflected in the precise quantum state of that surface, even though to a classical observer the horizon looks smooth and featureless. We do not yet know how to generalize this exact holographic dictionary to a universe like ours, with positive cosmological constant and a messy particle content. There is active research exploring versions of holography for de Sitter space, for cosmological horizons, for realistic models. But the core lesson from black holes seems robust. In any theory that combines quantum mechanics and gravity, the bookkeeping of information is more naturally tied to areas than to volumes. This is a profound shift in intuition. For most of physics, space is a container, and the action is in the contents. Here, the container's surface is where the story is written most economically. The bulk is, in a sense, a way of reading that story. There are different ways to picture this without leaning too hard on images that become misleading. One is to imagine that the interior of a black hole is like the inside of a novel, and the horizon is like the book's cover, plus all its pages pressed into a single plane. For an outside reader, the only things you can touch are the cover and spine. The holographic principle says that, in principle, the entire plot, every character and twist, could be reconstructed from the pattern inscribed on that surface, even if you never open the book. Another way, used by some theorists, is to think of space-time itself as emerging from patterns of entanglement. Quantum entanglement is the non-classical correlation between parts of a system that cannot be described by local properties alone. In some toy models of holography, the geometry of space, the very fact that points are near or far from each other, appears as a reflection of how strongly different degrees of freedom are entangled. Change the entanglement, and you change the geometry. In that view, the area scaling of entropy is less mysterious. The boundary between a region and its complement is where the entanglement is cut. The number of entangled links that cross that cut scales with the size of the boundary, not the volume. The black hole horizon is then an extreme case of a more general fact. The frontier between here and elsewhere is where informational richness concentrates. All of this helps with the information paradox, but it does not fully resolve it in a way everyone agrees on. There are still sharp questions about how information gets out during Hawking evaporation. Does it ride out on subtle correlations in the radiation? Does it involve some breakdown of the classical picture of the horizon, such as the speculative firewall proposals that replace the smooth horizon with a violent membrane? Does it require a new understanding of how interior and exterior degrees of freedom are related, as in the idea that wormholes and entanglement are two sides of the same coin? What almost everyone in the field agrees on is this: a simple picture in which information disappears into a singularity, and Hawking radiation is perfectly thermal, is not acceptable. Unitarity, the principle that quantum evolution preserves information, has survived every other test. Sacrificing it here would be like burning the foundations of the theory to save the house. So instead, many physicists now think the paradox is teaching us something about space-time itself. The fact that a black hole's entropy is proportional to area that its information fits on its surface is not a curiosity, it is a signpost. It tells us that the familiar continuum of space and time is not fundamental. Somewhere beneath it is a finite, discrete set of degrees of freedom, organized in such a way that volume is a derived concept, and area is the more basic currency. If that is true, the existential consequences are subtle. It means that when you look around a room and see three dimensions stretching away, you are seeing a useful approximation, not the raw architecture. It means that the story of a star collapsing into a black hole and the story of the horizon's area increasing are two ways of describing the same reorganization of information. It means that the intuitive divide between inside and outside is less absolute than it feels. From a human vantage point, none of this changes how it feels to stand under the night sky, or to watch a loved one sleep, or to make coffee. The world is still three-dimensional. Time still seems to flow, but in the background, in the theories that let us calculate and predict, there is now this quiet, unsettling suggestion. The deepest description of reality may be written on a surface we cannot see, and we may ourselves be features in that script. Black holes did not just force us to admit that there are regions where gravity is extreme and time behaves strangely. They forced us to reconsider where the universe keeps its books. And they hint that when we ask what is really real, the interior bulk we move through, or the boundary where information is stored, the most honest answer, for now, is that we are still learning how to read the hologram. If information, and even geometry itself, might be written on invisible boundaries, it is natural to wonder what else is hiding just off stage in the same equations, waiting in the wings like characters from a story that may never be performed. One of the strangest of these characters is something almost no one expected to find when they first drew the full space-time diagram of a black hole. When you extend the simplest Schwarzschild solution as far as the mathematics will allow, you do not just get a region that behaves like a black hole in the future, you also get a mirror image in the past, a region from which everything must emerge and nothing can ever enter. That mirror is called a white hole. If a black hole is defined, in rough language, as a place you can go into but never come back from, a white hole is defined as a place you can never go into at all. World lines, the paths that particles can follow through space-time, all point outward from its horizon. There is no way to send anything in, not even light. In the eternal Schwarzschild space-time, the solution that exists forever and is perfectly symmetrical in time, the Penrose diagram shows four regions. One is the familiar exterior, where an observer can orbit or fall in. One is the black hole interior, where all future paths end at the singularity. One is a second asymptotically flat exterior, often nicknamed another universe. And one is the white hole region, a shadowy wedge in the past from which matter and light spill outward, but into which nothing returns. This construction is mathematically self-consistent. It is what you get if you ask, How far can I extend these equations if I assume perfect symmetry and no collapse process? Just an eternal object. The white hole is the time reverse of the black hole. If you filmed a star collapsing into a hole and then played the film backward, the time-reversed version of general relativity would happily describe a white hole spewing a star into existence. The trouble is not with the algebra. The trouble is with the arrow of time. In our universe, entropy increases. Eggs break, but do not spontaneously reassemble. Smoke spreads out, but does not gather itself back into logs. Black holes form from the collapse of stars and other matter configurations, but we never see a black hole spontaneously uncollapsing into a star and ejecting a coherent stream of matter. The white hole region in the eternal solution represents precisely that sort of process. It is a universe that begins in a highly ordered state, with matter already arranged so that it will emerge from a horizon in just the right way. Nothing in Einstein's equations forbids such initial conditions. They simply seem wildly unnatural given what we know about thermodynamics. To create a white hole, you must not only satisfy the local laws, you must also conspire to set up an enormously special global state. For that reason, most physicists treat white holes as ghosts of the mathematics. They are there in the most symmetrical, extended solutions, but they are almost certainly not realized in any realistic astrophysical scenario where stars form and die, gas clouds collapse, and black holes grow over time. The actual black holes we see in the sky are born from collapse. Their past is filled with messy, increasing entropy, not with pristine white hole ejections. Still, the concept is hard to let go of entirely. In some speculative proposals, people have asked whether the Big Bang itself could be thought of, in some sense, as a kind of white hole, an initial state from which matter and space pour outward, with no prior region to fall in from. The analogy is tempting but dangerous. Our cosmological horizon is not the same as a black hole horizon. The global geometry of an expanding universe is different from that of a Schwarzschild black hole. Any identification between the two is, at best, poetic and, at worst, misleading. If white holes sit at one edge of the ghostly menagerie, wormholes sit at another. The idea that space-time might connect distant regions through a tunnel is older than the word wormhole itself. In the 1930s, Einstein and his collaborator Nathan Rosen noticed that the extended Schwarzschild solution can be interpreted as two asymptotically flat regions joined by a sort of bridge. On a space-like slice, this bridge looks like a throat connecting two mouths. It came to be called an Einstein-Rosen bridge. At first glance, that sounds like a shortcut. Perhaps you could enter the throat from one side, travel through, and emerge in the other region, having bypassed a long trip through normal space. Science fiction adopted that image eagerly. The catch is that the Einstein-Rosen bridge is not stable in the classical theory. It pinches off too quickly. Any attempt to send matter through causes the throat to collapse before a signal can traverse it. The bridge connects two regions of the full space-time diagram, but there is no time-like path that allows an observer to go from one exterior region through the throat to the other and then back out into the future. Later, in the 1980s, Kip Thorne and his colleagues played a different game. They asked, as a kind of disciplined speculation, what would be required to have a traversable wormhole, a tunnel in space-time that can actually be crossed by observers moving slower than light without hitting a singularity or a collapsing neck. They wrote down example geometries that satisfied the basic requirements of general relativity and had no obvious pathologies like closed time-like curves in the region of interest. In almost every case, one ingredient kept appearing. You needed matter that violates the usual energy conditions. In plain language, you needed some form of negative energy density, something that, in a given frame, has less than zero energy, or at least behaves that way in its gravitational effect. Ordinary matter and radiation do not do this. They curve spacetime in a positive, attractive way. Quantum field theory does allow small, local violations of the classical energy conditions. The Casimir effect, for instance, in which two conducting plates placed close together in a vacuum feel an attractive force due to the change in vacuum fluctuations, can be described in terms of negative energy density between the plates relative to the outside. But these effects are tiny and constrained. They do not come close to providing the sustained, macroscopic negative energy you would need to prop open a human-sized wormhole throat. So again, we are left with a split verdict. Wormholes are perfectly legal inhabitants of the equations. Traversable wormholes require exotic matter that we have no evidence for at useful scales. Non-traversable wormholes, like the Einstein-Rosen bridge, may exist in the sense that the maximally extended black hole solution contains them, but they cannot be used as cosmic subway tunnels. In recent years, wormholes have resurfaced in a more subtle role, connected to the holographic ideas we touched before. The suggestion, often summarized in 3 letters, ER equals EPR, runs roughly like this. The same mathematics that describes an Einstein-Rosen bridge connecting 2 black holes can also be used to represent the pattern of quantum entanglement between 2 systems. The letters ER stand for Einstein-Rosen and EPR for Einstein-Podolsky-Rosen, the famous thought experiment about entanglement. In this view, a wormhole is not so much a physical tunnel you could fly a spaceship through as a geometric way of drawing the entanglement between 2 otherwise separate regions. 2 entangled black holes might be thought of as being connected by a non-traversable wormhole in a higher dimensional description. No signals can pass through, so there is no faster-than-light travel. But the picture helps organize our thinking about how interior and exterior degrees of freedom might be related. This is still an active, speculative area of research. It lives in the intersection of quantum information theory, gravity, and high-energy physics. It is not a set of instructions for building stargates in a laboratory, but it does show how the ghosts in the mathematics bridges multiple exterior regions. White hole patches can sometimes acquire new meaning when we view them through the lens of quantum theory. There are other such ghosts, solutions with rotating cylinders of matter that drag spacetime around enough to allow closed time-like curves. Cosmological models, like Kurt Gödel's rotating universe, in which you can travel into your own past along certain paths. Exotic wave solutions in which spacetime undulates in ways that defy simple visualization. In almost every case, when you push on these constructions, you find reasons to doubt they exist as large-scale features of our universe. They require unrealistic distributions of matter, or unstable configurations, or initial conditions that are so fine-tuned they might as well be miracles. Some physicists have conjectured that there is a kind of cosmic censorship at work, that nature somehow hides or forbids the most pathological solutions, covering up naked singularities behind horizons and preventing time machines from forming. Cosmic censorship itself is not a theorem. It is more of a guiding suspicion, motivated by the absence of observed violations and by the behavior of many collapse simulations. We do not have a general proof that naked singularities cannot form or that closed time-like curves cannot appear. We simply have a growing catalogue of reasons to suspect that if they do, it is only in regimes where quantum gravity, not classical relativity, is the right language, and there our tools are not yet sharp. What all of these mathematical apparitions have in common is this: they show us the edges of our theories. A white hole reveals the tension between time-symmetric equations and asymmetric boundary conditions. A wormhole shows how geometry can, in principle, connect distant regions, and how energy conditions tie that connectivity to the nature of matter. Closed time-like curves warn us that causality, the simple rule that effects follow causes, is not automatically built in unless we demand it. From a distance, it might seem disappointing that so many of these creatures are likely confined to paper and blackboards, no traversable wormholes to other galaxies, no white holes ejecting stars, no time loops to revisit yesterday. But their value is not in their likelihood. Their value is in the questions they force us to ask. When you write down a solution with a white hole, you are forced to be explicit about why you trust the second law of thermodynamics, and why you think the universe began in a low entropy state. When you analyze a wormhole throat and find that it needs negative energy, you clarify what kinds of matter are allowed in your theory and why quantum inequalities restrict them. When you study spacetimes with closed time-like curves, you sharpen the meaning of causality and the role of global structure. In that sense, white holes, wormholes, and their cousins are like thought experiments that escaped the laboratory and took up residence in the field equations themselves. They are mathematical ghosts in the house of gravity, and paying attention to them has already led to new insights into holography, entanglement, and the deep relationship between geometry and information. The important thing, from the perspective we have been taking in this journey, is not whether these ghosts exist as literal places you could visit. It is that their presence in the equations reminds us that our current picture of space-time is provisional. General relativity, powerful and beautiful as it is, allows more than the universe seems to use. Quantum theory, equally powerful, resists the clean, classical causal structure we try to impose. Black holes sit at the intersection of those tensions. Around them, in the diagrams and the algebra, the ghosts gather. Some, like white holes, are probably artifacts of idealization. Some, like wormholes, may be reinterpreted as symbols of entanglement. All of them whisper the same message. The map we have is not yet the territory. There are features in the geometry that we can draw, but do not yet know how to reconcile with a world that has an arrow of time, a flow of entropy, and a stubborn respect for cause and effect. If the equations themselves are haunted by ghosts, then somewhere you have to ask a harder question. What happens at the places where those equations simply stop speaking at all? A singularity is a polite way for a theory to say, "I do not know." On paper, it appears as an infinity. Curvature grows without bound. Densities diverge. The mathematics that worked so well everywhere else returns nonsense at a certain point or along a certain surface. In school, you might meet a tame version of this in a simple function that blows up at some value of its argument. In gravity, the stakes are higher. In Newton's theory, point particles already carry this kind of danger. If you compress a mass into a point in that older framework, the gravitational force near that point tends toward infinity. The potential well becomes bottomless. Physicists learned not to panic. They treated that infinity as a sign that the model breaks down at very small distances, and they expected a better theory to repair it. General relativity replaced Newton's gravity with geometry. For a while, it seemed as if this upgrade might also tidy away the worst singularities. The theory already softened some infinities. It made the speed of light a strict limit, removed instantaneous action at a distance, and replaced arbitrary forces with geodesics in curved spacetime. But when people began to look seriously at what happens during gravitational collapse, the old problem returned in a new form. The Penrose-Hawking singularity theorems, developed in the 1960s and 70s, formalized this discomfort. They did not rely on special symmetries or idealized stars. They used very general assumptions about matter obeying sensible energy conditions and about spacetime, containing trapped surfaces where light is forced inward. Under those broad conditions, they showed that geodesics' idealized paths of freely falling particles and light rays cannot be extended indefinitely. Somewhere in their future or their past, they come to an abrupt end. In the language of the theory, that end is a singularity. It is not a point you can draw with a finite curvature and a finite density. It is a place where the mathematical description simply ceases to be defined. In the diagram, the lines stop. There are different reactions you can have to this. One is to shrug and say that the singularity is simply part of reality. Perhaps there really are points or regions where curvature becomes infinite, where notions like distance and time lose meaning. And that is that. Another reaction is to treat the singularity as a signpost that says, your theory is no longer applicable here. By that reading, the theorems are not telling us about what space-time is at those places, but about where general relativity, taken alone, reaches the edge of its useful domain. Most physicists have chosen the second reading. They do not doubt that black holes really form when massive stars collapse, or that space-time becomes very strongly curved inside them. But they suspect that long before the curvature literally diverges, and long before densities truly reach infinity, Quantum effects in gravity must become important. At those scales, general relativity, which treats space-time as a smooth continuum, is no longer the right tool. Quantum mechanics and quantum field theory, however, bring their own difficulties. They work beautifully on fixed backgrounds, where space and time themselves are given. They tell us how fields fluctuate, how particles scatter, how atoms form and decay. But they treat gravity, when they include it at all, as just another field on that backdrop. When you try to quantize gravity in the same way as other forces, you run into infinities that cannot be tamed by the usual renormalization techniques. So we have two extraordinarily successful frameworks. One says, gravity is geometry. Follow geodesics until they end. The other says, evolution is unitary. Information is preserved. Probabilities add up to certainty. Put them together around a black hole and they give conflicting answers. Near the horizon, general relativity tells you that space-time is smooth and that an infalling observer will notice nothing special as they cross. Quantum field theory tells you that the vacuum looks different to different observers, but that locally, physics reduces to the ordinary rules of special relativity. Hawking's calculation adds that, as seen from far away, the black hole emits thermal radiation. Inside, general relativity insists that all time-like paths end at the singularity in finite proper time. Quantum mechanics whispers that the wave function of the universe should evolve smoothly through all of this without erasing information. The singularity is not just a place where the curvature grows, it is the point where these two stories collide. The information paradox, which grew from Hawking's evaporation result, is one way that collision becomes explicit. If the radiation is exactly thermal, it carries no imprint of the detailed state of the matter that fell in. If the black hole evaporates completely, you are left with a featureless, mixed state. A pure quantum state has apparently evolved into something less pure. That is not supposed to happen. Many proposed resolutions of the paradox live at the boundary between gravity and quantum theory. Black hole complementarity suggests that no single observer ever sees a violation. From the outside, information is encoded on the horizon and radiated away. From the inside, an infalling observer experiences nothing dramatic at the horizon and carries the information to the singularity. You cannot compare notes, so there is no paradox for any one observer. Other ideas are more radical. The firewall hypothesis suggests that, to preserve unitarity and local quantum field theory outside, the horizon must actually be a violent place for infalling observers. Instead of a gentle crossing, they would encounter a searing wall of high-energy quanta. This directly contradicts the equivalence principle, one of the cornerstones of general relativity, which says you cannot locally distinguish free fall from inertial motion. Still, other proposals lean harder into holography. In those views, the interior of a black hole is not an independent region at all, but a way of talking about degrees of freedom already encoded on the horizon or on some distant boundary. The apparent conflict between interior and exterior descriptions becomes a bookkeeping issue. Wormholes, entanglement, and non-local connections between different parts of the system play a role in some of these constructions. What all of these attempts have in common is that they are trying to protect two principles at once: the success of general relativity in describing space-time outside singularities, and the success of quantum mechanics in preserving information. The place where this double loyalty becomes hardest to sustain is the black hole interior. That is where the classical theory insists on an end to time-like paths, and the quantum theory insists on seamless evolution. You can see the same pattern if you look at the very beginning of the universe. The standard cosmological model, when traced backward, leads to a Big Bang singularity, a moment when the scale factor of the universe goes to zero, densities diverge, curvature blows up. Again, the most honest thing to say is probably not that the universe literally began in an infinitesimal point of infinite density, but that the classical equations are being asked to do a job beyond their remit. In both cases, black hole singularities and the initial singularity, the breakdown is not a failure of fit to data. General relativity describes the motion of planets, the bending of light, the timing of pulsars, the ring-down of merging black holes, all with extraordinary accuracy. Quantum theory describes atomic spectra, particle collisions, solid-state phenomena, and much else with equal precision. The breakdown is conceptual and structural. It is as if you have two maps of the same territory, each excellent in its own region. One shows you the high roads, the large rivers, the coastlines. The other shows you the footpaths, the small streams, the soil types. Near the black hole, you need both levels of detail at once. Instead, the maps disagree. At the places where the disagreement is sharpest, the paper tears. From an existential point of view, this is where black holes become more than exotic astrophysical objects. They are not just places out there where gravity is strong. They are the laboratory, natural and inescapable, where our best theories confess that they are approximations. There is a kind of honesty in the infinities that appear in the equations. Infinity, here, does not mean exactly this big. It means the theory is being pushed beyond its trusted domain. When curvature scalars diverge, when geodesics become incomplete, when quantum fields in curved spacetime give ambiguous answers, the right response is not to worship the infinity, but to look for a deeper description. Candidates for that deeper description exist: loop quantum gravity, string theory, causal set approaches, asymptotic safety, and others. Each tries, in its own way, to quantize space-time or to replace it with more fundamental entities from which geometry emerges. Each has had partial successes and stubborn puzzles. None has yet produced a universally accepted, experimentally confirmed theory of quantum gravity. In the meantime, black holes continue to merge, accrete, and radiate, unconcerned with our theoretical discomfort. They sit at galactic centers and in X-ray binaries. They ring in gravitational waves and cast shadows in radio images. They also sit, conceptually, exactly at the juncture where our descriptions are guaranteed to fail if pushed too far. There is a quiet humility required to live with that. We like to think of science as converging on a final picture, a clean set of equations that will describe everything. Black holes remind us that each advance also reveals new edges. The success of general relativity did not close the book on gravity. It opened the chapter in which quantum gravity became a necessity. Hawking's calculation did not complete the story of black holes. It framed a paradox that has been driving research for decades. Seen in this light, the most important fact about black holes may not be any particular property we can list, but their role as markers. Wherever one forms, the message is the same. Here is a place where your current understanding, no matter how predictive and elegant, will eventually run out. Here is a boundary beyond which your theories must change or be replaced. And because these markers are not abstractions but real objects that the universe makes and uses, they carry a further implication. Our incompleteness is not an accident of our perspective. It is written into the cosmos itself. It is one thing to know, in the abstract, that our best theories are incomplete. It is another to live in a universe that keeps placing those limits in real, heavy objects you can point a telescope at. Black holes sit in that uncomfortable space between what we can describe and what we can only gesture toward. For a long time, it was easy to keep them at arm's length. They were curiosities in textbooks, background threats in science fiction, metaphors for depression or greed or oblivion. You could talk about them without really letting them touch how you think about being alive. That distance has been eroding. Some of the erosion is technological. At the beginning of the 20th century, the phrase black hole did not exist. Gravity was a smooth curve in Einstein's equations, not a trap. By the middle of that century, the idea of collapse had emerged, but the objects themselves were still unseen. Now, in the space of a few decades, the situation has inverted. We have watched stars near the center of the Milky Way swing around an invisible mass, and from their motions we have weighed the black hole that sits there. We have listened to the space-time around merging black holes ring like a struck bell, and from that ring we have inferred their masses and spins. We have seen the silhouette of a horizon in the glowing gas around M87 star and Sagittarius A star. Each of those achievements came from teams of people working for years or decades, building instruments and theories, arguing over noise, calibrating mirrors, analyzing faint signals. Each one could be described in technical terms as a progress report in astrophysics. But if you allow yourself, for a moment, to look past the technical language, there is also a quiet shift underneath. A creature that evolved to judge the ripeness of fruit and the intentions of other faces now has the means to photograph the edge of a region where time slows nearly to a stop. A brain that once had to guess at the weather next week now can reconstruct the last orbits of two invisible black holes more than 1 billion light-years away from a subtle wobble in the length of a laser beam. We do not fully understand what a black hole is. We do not know exactly how quantum gravity resolves the singularity, or how information leaks out during evaporation, or whether the holographic principle in its current form is the right path to a deeper theory. And yet, with all of that ignorance intact, we can still measure, predict, and hear. That combination of deep not knowing and precise partial knowing is where the existential weight lies. On one level, black holes continue the long process of decentering us. Copernicus pushed Earth away from the center of the cosmos. Later astronomers showed that the Sun is one ordinary star among many in one ordinary arm of one galaxy. Now we know that at the center of that galaxy there is a dark object weighing millions of solar masses, and that at the centers of other galaxies there are black holes weighing billions. Our solar system is a peripheral swirl in a much larger gravitational story. Over immense timescales, the dynamics of that story will be shaped less by individual stars like the Sun and more by the slow evolution of these central black holes and their feedback on galactic gas. On another level, black holes draw us closer to the center of something else. They mark the places where our picture of the universe is thinnest, where our theories are most visibly provisional. To study them is to stand where two great rivers of thought meet: the geometric vision of general relativity and the probabilistic unitary world of quantum mechanics. You can feel that meeting point in the history. In the year 1965, Roger Penrose showed that, under very general conditions, gravitational collapse leads to singularities. He took away the option of treating black holes as mere mathematical accidents. In the year 1974, Stephen Hawking showed that quantum fields in curved spacetime make black holes radiate and evaporate. He turned them from final sinks into thermodynamic systems with temperatures and entropies. In the year 2016, the first direct detection of gravitational waves announced that binary black holes are not rare curiosities but common players in the universe. In the year 2019, and again in the year 2022, the Event Horizon Telescope gave us images of black hole shadows. None of these moments gave a final answer. Each one opened new questions. Penrose's theorems forced us to accept singularities, and then to ask what replaces them in quantum gravity. Hawking's result forced us to ask how information is preserved. Gravitational wave detections forced us to ask how such massive binaries form and what they say about stellar evolution and maybe about primordial black holes. The EHT images forced us to refine our models of accretion, magnetic fields, and plasma in strong gravity. The pattern that emerges is not one of conquest, but of deepening involvement. We are not closing the book on black holes. We are becoming part of a longer story in which our questions are themselves a feature of the universe's self-understanding. It is easy to slip into grandiose language here, to say that the universe is looking at itself through us. But we do not need that metaphor. It is enough to notice the more modest, but still astonishing, fact that the laws we infer in our small laboratories seem to hold in the violent environments around black holes. The same quantum field theory that describes scattering events in accelerators underlies Hawking radiation. The same general relativity that describes the orbit of Mercury describes the ring down of a merger billions of light years away. This coherence is not guaranteed. It could have been otherwise. We could have found that our theories failed chaotically as we moved to new scales, that nothing learned in one regime applied to another. Instead, we keep finding that the universe lets us reuse our tools, with modifications, in places far removed from where we invented them. From that perspective, black holes shift how we see ourselves in at least three ways. First, they change our sense of scale. Distances, masses, and timescales involved in their lives stretch our imagination. The fact that a black hole can outshine a galaxy while feeding, that a supermassive black hole can take longer than a trillion years to evaporate, that gravitational waves can cross hundreds of millions of light years and still be measurable, puts our own lifespan into a different frame. Not to belittle it, but to place it. Second, they change our sense of certainty. For centuries, physics has often been presented as a progression toward ever more complete, ever more unified explanations. Black holes make visible the seams. They show us, in an operational way, where our current frameworks cannot both be right as they stand. That does not mean we should retreat into nothing can be known. It means we can hold two attitudes at once: trust in the parts that work astonishingly well, and openness about the places where they fail. Third, they change our sense of what counts as a meaningful question. Asking what happens inside a black hole is not like asking what is north of the North Pole. It is not a category error. It is a demand that we extend or revise our basic concepts of space, time, and information. In grappling with that demand, we have discovered holographic dualities, deep connections between entanglement and geometry, and new links between quantum information theory and gravity. Questions that once sounded metaphysical about reality, about locality, about the nature of nothingness, have acquired precise, technical forms. None of this fixes the human problems that fill our days. Black holes cannot tell us how to be kind, or how to build fair institutions, or how to carry grief. The universe does not hand out moral lessons with its gravitational waves, but there is a softer influence. To really sit with the fact that there is a horizon at the center of the Milky Way, and that we have imaged its shadow. To really sit with the fact that there are black holes colliding in distant galaxies, and that their collisions shake space-time in ways we can hear. To really sit with the fact that our best theories insist they will one day evaporate into faint radiation. This has a way of loosening certain kinds of arrogance and sharpening certain kinds of care. Arrogance, because it becomes harder to believe that our current ways of carving up the world, our nations, our economies, our doctrines, are ultimate. We live in a universe where even the concepts of inside and outside, before and after, are, in some regions, negotiable. Care, because you begin to see how contingent our vantage point is. There is a narrow window of cosmic conditions in which beings like us can exist. Not so early that everything is just plasma and noise, not so late that only black holes and Hawking radiation remain. In that window, we have managed to learn enough about the universe to notice its strangest inhabitants. If you happen to be listening to words like these at night, perhaps with the light low and other people asleep, you are participating in something quietly rare. A small patch of chemistry on one planet, briefly aware not only of its immediate surroundings but also of invisible structures millions or billions of light years away, and of the fact that those structures expose the edges of its own understanding. Black holes, in that sense, are not just out there. They are part of the background against which we draw a picture of ourselves. They remind us that the universe allows extreme states we can barely imagine, and that our minds, built from ordinary matter under ordinary conditions, can nevertheless reach toward them with equations, instruments, and stories. The most amazing fact about black holes may not be any single detail we have listed: their density, their temperature, their entropy, their ability to merge or to seed galaxies. It may be this: they force us to keep two truths in view at once. One, that we are very small. Our lives are brief. Our bodies fragile. Our home a thin film of water and rock orbiting a mediocre star in the outskirts of one galaxy among many. Two, that being small does not mean being irrelevant. In the time we have, we are capable of understanding, with real precision, some of the most extreme phenomena the universe produces. We can map their shadows, decode their waves, argue about their information content. We can let them change the questions we ask. Between those two truths, there is room for a different kind of humility, not the kind that says we are nothing, but the kind that says we are something, and that is astonishing enough. Black holes do not care what we make of them. They will continue to form, merge, and very slowly evaporate, regardless of whether anyone is watching. But as long as there is a species on a small world that can listen and look and wonder, they will occupy a special place in our inner universe as well. Not as monsters, not as final answers, but as quiet reminders that reality is deeper, stranger, and more open than our first instincts suggest.